So hello and welcome student to today's lecture. So this is our course MA412 linear algebra, and today is the lecture number 8. Okay. So now recall that we defined last LVW space of linear maps between two vector spaces V to W over the same field F space of linear maps from V to W. Okay, and for when both domain and codomain are same V, then we write down LV for LVV, and this will be we call the space of linear operators. So the elements of linear maps from V to V we call operators. Okay, so space of linear operators. Yeah, so now we are going to actually discuss there's something called algebra structure on it. So algebra is what algebra. So this is already we learned that LBW or LBB or LB, these are actually vector spaces, right? So we are planning to also define a ring structure on this LB, and for the we need some multiplication, right? So what is the natural multiplication on these maps? That is called composition, right? Now the natural question is that does the compositions are also linear maps? So like if we have two compositions, so you can ask question, does composition of two linear maps again linear? So you can ask this natural question, and the answer is yes. So yes. So let me just write down maybe in the terms of theorems. Suppose you have two linear maps, say T1 from V2, maybe V1 to V2, and you have T2 say from V2 to V3. So you have three vector spaces over the same field F. So all are over the same field F. Okay, I am not writing again and again. Okay, so in this case one can ask what about T2 compose T1. So this is the compose sign. Maybe we will just write down this as T2 T1. Okay, without forgetting the composition. Okay, so this will be a map from V1 to V3, right? So you can ask naturally whether this composition is also a linear map or not over the same field. Okay, the answer is yes. So how to check their linear map? So what you need to check two linear maps? So you choose two elements, say U and V belongs to V1, and you choose a constant, say C belongs to the F. Okay, now let us try to find out what happens when you evaluate this T2 T1 on say CU plus V. Okay, whether it satisfy the properties of linear maps or not, and the equivalent properties. Now so composition means what? That means T2 of T1 of CU plus V, right? Now we know that so we know that T1 is linear. So what does that mean? That means T1 will satisfy the linearity property, and that tells you that this will be C times T1 of U plus T1 of V. Okay, so this is by linearity of T1. Okay, now similarly T2 is linear. So what does T2 do? T2 is additive, and also we multiply by the constant compounded. So this is C of T2 T1 of U plus T2 T1 of V, right? What does that mean? That means this is actually nothing but C T2 T1, the whole thing of U plus T2 T1, the whole thing of V, right? V, and hence the composition T2 T1 is again linear, right? So you can obviously so that means that you can define so in particular when you are LV, so in LV we have one more operation, right? So what does that mean? That means you can have a map from this composition that will be mapped from LV cross LV to LV, right? So in LV you already have addition and scalar multiplication, which makes LV a vector space. But you have a composition that will give you ring structure. Okay, and what is the map? The map is that you choose two elements here, T1 and T2, and send it to T2 compose T1, okay, or T1 compose T2, doesn't matter, okay? Something like that, okay, which is we write down T2 T1. So now we need to check that whether this operation exists because of this theorem, that is linear, right? The question is that whether this operation satisfy the properties of rings or not. So that means whether they distribute over addition, other things or not. And here is a theorem. So that theorem tells you that okay. So we will show that we will show that this LV has algebra structure. So what does that mean? That means this is both vector space and ring. I hope you have learned what is the ring in your undergraduate studies in group theory in algebra. Okay. So I'm assuming that you know that. But if you don't know, then we can discuss on our live classes next week. Okay. So and that obvious, just this theorem will tells you that. So for example, you choose three maps T1 and T2. They are element of say LV. Then what happened? Then these are true. Then number one, if you just first add T1 plus T2 and then compose with T, this will be individual composition and then addition T2. Okay, and that is true for all T1 T2. This is for all for any. And this is not only true for one side, this is true for both sides. That means you can do it from this side also. And this will be then T1 T plus T2 T comes, right? This is for all T1 T2. Okay. And So that means what? That means this composition is distributing over addition. Okay, this is the meaning. And if you have this kind of if you compose say cylinder around T2 T1, doesn't matter T2 T1 T2. So this is actually satisfies this kind of associative property. So T2 and then T1. Okay, and not only that, this is for any identity operators. So identity operators, T of I is nothing but I of T is actually equal to T. So if you compose the identity operator, it will be the same operator. Okay, and even for scalar multiplication also. So this is true. So what does that mean? That means for any constant C, T2 T1 is nothing but C times T2 of T1 also is equal to T2 compose CT1. Okay, so this is for all C belongs to F, the scalar field. Okay, and these proofs are very simple. You just use the linearity property of T1 T2 and then done. So that theorem tells you that LP is a algebra. Okay. So the natural question what one can ask that when you take a composition, then we already learned that if you have learned about the matrix representation, right? Now when you add to linear transformation, the matrix representation with any basis will be the addition of individual matrix representation with respect to the same basis, right? Now what happens when you take the composition? It's a natural question, right? So what will be what is the matrix representation of composition of two linear operators? Okay, and let us see the answer. So let us discuss, then we will understand what is happening. So what I'm assuming that these three vector spaces are the V1, and then you use T1 to go to T2, V2, and then use go to T2, right? Using T2 to go to V3. Okay, so these are linear operators T1, T2, and let me assume that the basis of V1 is something say V1, and maybe let me write down something. What should I write down? So something V1 up to Vn, and basis of this equal to V2. Maybe this is okay. So this is in general. I am just saying. Okay, so I am not assuming that they are same dimension. They are all finite dimensional, but they may not be the same dimension. Okay, so maybe this is W1 to say Wm dimension m, and basis of V3 equal to say V3, and this is something say Vw. You can write down what you write down, say U, maybe U1, U2, something say UP, dimension P. Okay, so this is n dimension, this is m dimension, this is p dimension vector spaces over the same field F. Okay, now question is that if you know that matrix representation of T1 with respect to B1, B2, and T2 with respect to B2, B3, can you say about the composition? Okay. Let's see what we can say about this. So let me write down also, maybe say A1 is that matrix of T1 that we already know with respect to B1 and B2. Okay, and say A2 is nothing but matrix representation of T2 with respect to B2 to B3. Okay. Suppose this is known to us, and if it is known to us, then what will be the what will be the representation of the compositions? Okay, T2 compose T1. So how do you show? So the obvious thing is that you start with T2 compose T1. You know that this is from V1 to V3, right? So I need to start with the basis of V1 and take the images and write down those in terms of basis of V3, right? This is the process. So you start with T2, T1, and then you take with Vj, jth element. So what will be the jth element of that? Jth element of that will be uh, okay. So okay. Before that, let me write down some more thing. Suppose this is matrix, no? So what does that mean? That means Aij. So you can write down T um, T1 of Vj, and that is say for example with respect to W, so you write down something summation Aij Wi equal to 1 to m. This true for all j equal to 1 to up to n, right? Because there are n many vectors in basis of v1. Similarly for matrix T2, so T2 you have to evaluate on that. So maybe let me write down but this is dummy vector, right? So for dummy vectors, what we can say, we can instead of I, let me write down k. That will be easier for us. Or is no problem. It's also same I k s m. So here let me write down T2 of say omega I summation. Maybe this is the matrix. Okay, so this is Aij, and this is B BKI. Let me write down by this. So what will happen? So this will be BKI, and then the UK. K is that this basis of B3, right? B3, which is element of B3, and here K is running from 1 to P. Okay, 1 to P, and your I is running from I is running from for all I equal to 1 to up to M. Okay, so these are the individual matrices. Then if you plug those things here, then what happens? So Vij, so this will be T2 of T1 Vij means what? T1 Vij is nothing but summation Aij and Wi, right? Wi I equal to say 1 to m. This is we already know from the matrix basis of T1. Now we know that T2 is linear. So what does that mean? That means so T2 is linear means if you apply linear property, so it will be Aij T2 of Wi and I equal to say 1 to m, right? Now T2 of Wi, that will be that we already know from matrix representation of T2 of Wi, and in this let's plug those things in here. Summation I equal to 1 to m Aij, and this is what this is B. See, this is B K I UK, right? So write down that. So summation UKI and UK k equal to 1 to p, right? So finally we wrote the elements of basis vectors of v1 in terms of uk, which are basis vectors of v3, right? So what does that mean? That means this is summation over the double sum, right? Double sum over I equal to 1 to m, and then k equal to 1 to p bki into ij. Okay, this is the full sum. I mean, maybe we can take inside sum outside. Okay, so maybe we will interchange. Okay, so next line. Okay, now interchange the sum. What we will give? So we will have in terms of k. So this is k equal to 1 to p summation I equal to 1 to m. Okay, and then b k I a I j and uk, right? See, this is exactly the in terms of matrix representation in terms of basis vector of v3, right? And k equal 1 to p. Now note that this sum is, what is this sum? Can you imagine this sum? So let me write down, this is something c k and I, because no, ckj. So yes, so k equal to 1 to p uk. Okay, now this is c. What is ckj? Ckj is where ckj is ckj is summation I equal to 1 to what? 1 to m b bki and then aij, right? bki, right? Exactly. So what does that mean? This is nothing but the matrix multiplication, right? So we have matrix aij, bik and bki, and then multiply them into this, right? So what does that mean? So this means that if you take this matrix representation, so that will be exactly nothing but the multiplication of individual matrices, right? So thus this T2 composed U1 with respect to the basis U1 V3, that will be equal to this individual composition of matrices. This is from V1 to V2, and this is from V2 to V3. Okay, so this is the theorem that tells you that is exactly satisfy the composition is exactly satisfy the matrix multiplication. Okay, so this theorem in particular, when you are in so you can say corollary. So for so if this T1 T2 are element of LV, then with respect to the so then there will be no B1 B2 B3, there will be only one basis, right? So that basis will be say B, which is your B1 B2 and B3, same, this will be same basis, right? And then with the same basis this matrix representation will be write down by the only one basis, there is no other basis, and that will be nothing but this product of individual matrices. So matrix representation of composition of two linear operators is nothing but the product of matrix representation of individual linear operators. Okay, this is a simple observation. Okay, so now maybe we can ask one more question, that okay, so yeah, so this is one corollary, and then another corollary you can easily check that that coordinate vectors are of this form. So this is another corollary, it's obvious corollary, so I am not going to give the proof. So if you have this linear operator T from V to W, okay, and suppose you know the basis say b1 here and b2 there, and you want to know what happened to any vector, so you choose any vector, say p or v, and you want to know what happened, so tv is element of w, so you want to know what is the coordinate standard coordinate vectors of tv with respect to the basis b2, and that will be nothing but the matrix representation with respect to b1 b2 with composition or multiply by the coordinate vectors, which is nothing but the column matrix of u with respect to here, so b1. Okay, so you can think this is one dimensional, like these column vectors are actually say n cross 1 matrices, right? So this is also multiplication, and that is straightforward coming from this theorem. You just apply this theorem. Okay, so these are the observations. With this observation, we are going to now okay, so with all these observations, maybe we will define something called maybe inlet multiplication transformation, or okay, so let me see. Okay, so now we will define some special kind of transformation, and then we will check that what happened to their corresponding matrices. Okay, so what is this kind of transformation? So suppose you have so already you know that given two vector spaces and in a map between these two things, there exists always a matrix that represents that with respect to basis, right? The converse is also true. You can you start with a matrix, then obviously with respect to some basis, the matrix must on the same basis. Okay. So also so now question is that can a matrix give a linear maps back to the operator? The answer is yes. So so how to do that? So suppose you choose a matrix A, which is element of say n cross n matrix over some field type. Okay, and then you can define actually. So you can talk about same cross n matrix means it is mapped from Fn to Fm, the other way around. Okay, Mn means n to m. So Fn is a vector space for F, what dimension n. So what is Fn? So Fn you can think about the Cartesian product of m times F cross, like you can think about this, right? N times. Similarly Fm. So what will be the map? So you define something called LA from Fn to Fm. And what is the natural definition? So you take A and you take a vector here in Fm. Okay, so maybe write down the vector V, and then you define is AV. Okay, so this is obvious. So here, so this is n cross n, and this is n cross 1. N cross 1 means n many columns and n many rows and one column. So this is column vectors, and it will be n cross n. So this will be again a column vectors here, right? And now this map is called, this is nice name, it's called left multiplication transformation. Okay, it's called the left, from left side we are multiplying. Okay, left multiplication. Multiplication. Linear maps or linear transformation, whatever transformation. It is easy to check that this is a linear map. Okay, and not only that, it has nice properties. So what are the properties? This is also very simple properties. You can easily check that. So I'm taking the standard error basis. So standard error basis means what? So that means okay, so here standard error basis of n is what? So this will be uh, dimension n, obviously. Okay, and this will be like 1 0 0 0. Okay, n, and then 0 1, second person is 1, and we will like this and so on, and last one will be 0 0 0, last one will be 1. So this will be standard error basis of fn. Similarly for fm also, with respect to these two standard error basis, b1 and b2. So let write down first, let b1 and b2 be the standard or the basis of this fn and fm respectively. Then the number one is what? So with respect to that, if you take, so this linear maps. So this is linear map. You can easily show this is homework, so that LA is linear. Okay. Now with respect to these two bases, beta 1 and beta 2, you check that the matrix combination of that will be exactly A. Okay. And this first property. Second property is what? So in particular, if you have if you define two such left transformation map, LA and LB, and you see that these maps are same, then this is true if and only if A equal to B. Okay. These are all simple observations, simple proofs. You can prove by your own. Similarly, if we add two such matrix A and B, then the corresponding left multiple transformation will be exactly LA plus B. So LA plus B will be nothing but LA plus LB. Okay. So similarly, if you take the product with some matrices where the product exists, obviously m cross n and n cross p, then when the product exists, whatever, then if you take the product, maybe A and C and the matrix m cross n and n cross p, then it will be nothing but individuals. So this will be LA and LC. Okay. And when these m and n are same on same dimension, then what happens when if m and n are same, then what happens then with respect to the identity matrix, suppose A equal to the identity matrix on the dimension n, this is exactly will be what? This is nothing but the identity map of Fn. So this linear map become identity map. Okay. So these are obvious properties you can use or application in these theorems. From these theorems and linear maps, you can easily prove it. Okay. So with the help of all those things, okay. So these are some properties. Now we are going to define the very important idea. It's called immutability. Okay. So let us define it. So of linear operator. and obviously okay, so how do you define? So or linear maps also, you don't need linear operators or linear maps. You can have different vector spaces also. So suppose so we have, say, suppose T1 from V to W. So a function something say T2 from W to V is um, um, is said to be an inverse. I mean, see, I'm so when I'm saying inverse, I mean that both sides are inverse of T1 if what happen if this T2 compose T1, which is from V to so you go V to W and W to V, so this will be mapped from V to V. So this has, okay, so this map is actually the identity map on V, and the other way also, T1 compose T2. So this is mapped from W to W, so this has to be identity map on W. If this happens, then we call T2 is an inverse of T1. But you can prove that this is actually the inverse. Okay, if it exists, this is always unique. And in this case, we write down T2 equal to T1 inverse by this. Okay, the simple definition. And obviously, the basic property tells. Okay, so definitely you can always, basic property tells you that if you have two maps, say T1, T2, and if you want to take inverse of that, that will be T2 inverse, T1 inverse. Okay, this is exactly the inverse of matrices, and the inverse of inverse will be the same. So T inverse of inverse, that will be T. These property are simple property. Okay. Now the important question is that whether if you start with the linear map, whether the inverse of that is linear or not. I mean, I'm assuming that is inverse exists. If the inverse exists, then what happens? Okay. So does this is question, does the inverse of a linear map is also means also invertible, as also linear. Linear map is also, so means also, or also linear, I should say. By also, so means they are also linear. Okay. So how to prove this thing? So answer is yes. So answer yes. When you talk about inverse of linear map, there has to be also linear, right? Now how to prove that? So the proof is like this. Now so you choose two elements, say so T is linear, is given V to W linear is given to you, right? Now T inverse is from W to V, right? I need to prove T inverse is linear. So what does that mean? I need to check with two elements from W and over the some field F. So let you start with any two, maybe V1 and V2 belongs to W, and some constant C belongs to F. Okay. Suppose this is this. Now okay. So invertible means there is also one on one, right? So this maps as pre-images. So what does that mean? So there exists some U1 and U2 belongs to V such that what happens, such that T of U1 will be V1 and T of U2 will be V2, right? This is the meaning of pre-images exists, right? This is on to map also. Now I need to check that. So what does that mean? That means T inverse of V1 equal to E1, T inverse of V2 equal to E2, right? So what I need to check? I need to check that T inverse of C V1 plus V2 should be equal to C times T inverse of V1 plus T inverse of V2, right? But what is this? This is C V1 is nothing but T inverse of E1. So this is, sorry, T of E1. So this is T of E1. And V2 is nothing but T of U2, right? And so what does that mean? That means you can use the linearity property of T that tells you that this is nothing but T of C U1 plus U2, because T is linear, right? Now the property of invertible maps tells you that T inverse T is nothing but identity. So that gives you identity here. So you will have C U1 plus U2, U2, yes. But what is U1? U1 is nothing but T inverse of V, right? So T inverse of V1. Similarly, U2 is nothing but T inverse of V2, T inverse of V2. Done. So that is actually tells you that T inverse of C V1 plus V2 is nothing but C times T inverse of V1 plus T inverse of V2. So that proves that the linear maps, if the inverse exists, then the inverse is also linear map. Okay. So this is very simple observation. Now again you can ask the question, same question, that what will be the matrix multiplication of the inverse of linear maps, and automatically answer will be exactly the inverse of the matrix. So what does that mean? That means so if we have T from V to W, and if you know that the basis of this is B1 and basis of this is B2, if you want to find out, you know that the matrix will be, say A is a matrix of this form from V to W, okay, and if you want to find out what is that matrix representation of T inverse, so T inverse means W to V, so it will be basis from B2 to B1. So what is the natural guess? The natural guess is nothing but, so this will be exactly, you take that original matrix with respect to B1, B2, and then do inverse, because this is the inverse of the original map, right? So the corresponding matrix will be also inverse to each other, and this is also the proof is obvious. So I'm just giving a homework. It's obvious proof. You take T inverse, then composition of identity matrix, you write down IV with respect to the same basis, either basis of V or basis of W, whichever identity you choose. And then this is obvious. Then you use the property that we prove somewhere here, that composition, matrix or composition is nothing but the product of the individual matrices, right? So that will be enough for tells you this. Okay. So now okay. Maybe okay. So let me just define one or two more property, and then we will stop here for today's things. Okay. Maybe one property I should say that if we have a linear map which is invertible, so maybe this property can also, maybe we can write down theorem kind of thing. So so you have this W is invertible linear map. Okay, suppose this is given to you, then obviously one is time dimensional plus another one is then dimension of v is less than infinity if and only if dimension of w is also finite. Okay, and not only that, they are same also. So and further in this case, when they are invertible, this dimension of v if they are finite dimensional, then in this case, for infinite dimensional, we cannot say anything. V equal dimension of w. Okay, and the proof is what? The proof is simple also. So just few observations you need to check. One thing is that if you start with say, suppose this is a basis of something, write down say v1 vn. So this is a basis of say v, and so if this is the basis of b, then and obviously it's onto. So what does it mean? That means onto means that that the range. So b2 will be what? So b2 will be t of v1 t of vn. So this will be exactly is a basis of w, because the range is here full w, because this is invertible, right? So onto also. So onto means the range is full w, and hence this is range is generated by this. So you can say, so not basis I should not say. So this is a generating set, you can say that. So this is a I should not say basis. Okay, I should say this is a generating set. Generating set of this, but that is okay, because if the generating set are finitely many vectors, then dimension of w also finite, thus dimension of w is also finite. So if you start with dimension of v finite, so this is a vector, this means the dimension of, I am assuming the dimension of v is finite, right? Some n, and that proves that dimension of w is also finite n, right? And conversely, same thing you can do that t inverse also. So dimension of, so the t inverse maps from w to v, and because if you start w is finite, then this is also finite. Okay, so if one part is finite, the another part is finite. So now the question is that why these two are same? So that obvious, because t is 1 means injective map, and you remember the property of injective map. So this implies the kernel of t is what? So a singleton, right? So that is that nullity t is nothing but 0, right? Now if nullity is 0, so rank of t will be the full, right? So rank of t, that will be dimension of v. But on the other hand, what is rank of t? Rank of t is nothing but dimension of the range space, right? So this is dimension of t of v, right? Which is nothing but dimension of v. But t is onto, so t of v is nothing but the w. So this is nothing but dimension of w. Okay. So what does that mean? That means if there is a linear maps, then these two vector spaces have same dimension. I am assuming that they are finite dimensional. Okay, then they are same dimension. Okay, so so these kind of linear maps also called isomorphisms. Okay, so how to define? So we write down by this. So let w and v be two vector spaces over some field f, So we say W is isomorphic to V, or V isomorphic to if there exists an invertible linear map. Invertible linear map from W to V or V to W, whatever, doesn't matter, from V to W. Okay, so these kind of linear maps are called isomorphism. So they are also called, an isomorphism of vector spaces. Okay, isomorphism of vector spaces. Clear? Okay, so now so there will be so obviously that the previous theorem tells you that if two vector spaces are isomorphic, that means if and only if the dimension is same for finite dimensional vector space. This is not true for infinite dimensional vector space, and that is obvious because of our last theorem. Okay, and you can also prove that any two. These are all simple observation. If so, let V be a vector space of the dimension n, over the field F, then V is actually isomorphic to Fn. Fn means that n cross F cross F cross n maintain, right? So these are a very simple observation. You can easily prove it. How to send? So you just send, take the basis here and send it to the standard basis there. That will be that immaterial maps. Okay. So finally, I think I will stop with the representation, which is called standard representation, with respect to some basis. So what does that mean? So you start with the ordered basis of some n vector space V. So let me write down. So B is a ordered basis of V over F, and then you can define something called representation or standard representation V with respect to this basis. So the standard representation of V. So we show that V and Fn are isomorphic, right? N is the dimension of V. Okay, so with respect to this V, so this is what, this is kind of a map generally defined by this map phi of B. So what is phi of B? Phi of B is a map from V to Fn. And what is the natural map? The natural map is that you take a vector here. This is very natural one. So you take a vector here, maybe say V, and you send it to the coordinate vectors here. Coordinate vectors are what? So coordinate is with the same basis. So V with respect to the same basis. Okay, and these coordinate vectors is kind of, you can think these are column vectors, element of Fn, and this is the natural isomorphism between V to Fn, what I was talking about. Okay. This is called the standard representation of V, which is a natural isomorphism from V to Fn. Okay, maybe I will stop here, and next day we will learn another very important idea. Okay, so stop here.